In this lecture, we want to discuss a special class of functions known as the hyperbolic functions. They are defined formally in terms of the exponential function as follows. Notice that these are composite functions. If you recall that e to the power minus t is the same as 1 over e to the t, then the numerator of the hyperbolic sign can be written as u minus 1 over u. So, the hyperbolic sign of t is f composition g, where g of t is e to the t, and f of u is 1/2 the quantity u minus 1 over u. For shorthand, we call the hyperbolic sign sinh and the hyperbolic cosine cosh. As we just did for the sinh, we can write cosh t is h composition g, where g is e to the t, and h of u is u plus 1 over u, all divided by 2. The domain of the function sinh t, which is f composition g, will be all points t in the domain of g, which is the exponential function, for which f of g of t makes sense, that is, g of t is in the domain of f. This composite will make sense as long as g of t is different from 0, since f of u is just the difference of u and 1 minus u, 1 over u rather, divided by 2. But e to the t is never 0, so the domain of the composite function f composition g is the entire real line. Now the range of the function g of t equal e to the t is the positive real numbers. So the range of the composite function sinh t equal f composition g is the range of f of u if u is restricted to positive values. We can graph f of u, which again is the difference of u and 1 over u divided by 2, for u positive. From the graph, you can see that the range of f of u with u positive is the entire real line, and that will be the range of the hyperbolic sign, sinh t. We can use the same approach to find the domain and range of the hyperbolic cosine, cosh t, which can be thought of as h composition g, whereas before g of t is the exponential function e to the t, and h of u is the sum u plus 1 over u divided by 2. As before, you can see that the values of g of t are always positive, and h of u would only be undefined if u were equal to 0, which never happens. So, also for cosh t, the domain is the entire real line. For the range of cosh t, you have to graph the function h of u, which again is u plus 1 over u divided by 2. Locating the minimum value is easy if you know calculus. If not, you can do some work with a graphing calculator to intuitively convince yourself that the minimum of h of u occurs when u is 1 and h of u is 1. From this we know that the range of h of u for u positive is the interval 1 infinity, including the point 1, and that will be the range of cosh t. You can then define analogs of all the other trig functions. For example, hyperbolic tangent, pronounced tench, is the ratio of sinh to cosh, and the hyperbolic secant, which I won't try to pronounce, is 1 over cosh. One question that occurred to you immediately is why study these new functions, and why do they have names modeled on the circular trig functions? Well, first to the names. Recall that if you locate a point with coordinates x, y on the circle of radius 1 centered on the origin, then x squared plus y squared is 1. If this point is located at an angle theta from the positive x-axis, then the coordinates of the point can be written cos theta sine theta. And that gives you the fundamental trig identity, cos squared plus sine squared is 1. Now look at the formulas we just gave for sinh and cosh, and compute cosh squared minus sinh squared. Notice the minus sign. So, for a given value of t, we locate the point in the Cartesian plane that has coordinates xy equals cosh t sinh t. And then x squared minus y squared is 1. but this is just the equation of a hyperbola. So just as we conclude that the points with trig coordinates cos t sine t always lie on a unit circle, the points with hyperbolic function coordinates cos t sinh t always lie on a special hyperbola, thus the names hyperbolic sine and hyperbolic cosine. The graphs of these two functions, sinh and cos, are next on our list. For large positive values of t, the term e to the t dominates and e to the minus t is negligible. For large negative t, the situation is reversed. Notice that sinh is odd, preserving its analogy with the sine function, and cos is even, analogous to the cosine function. Notice also how rapidly they both grow in size as t moves away from the origin. So now I need to convince you that these functions have some degree of importance. Well, here's one example. The catenary is defined as the shape of a perfectly flexible chain or cable suspended by its ends and acted on by gravity. Think of a chain or a cable suspended between the tops of two poles spaced a distance apart. If you live near a high voltage power line with those huge towers, just look at the shape of the electric cables between the towers. Galileo believed that this curve is a parabola. The great Swiss mathematician Jacob Bernoulli challenged the mathematical community to determine the equation of the curve. And the problem was solved independently by Leibniz, by Huygens, and by a relative of Jacob Bernoulli, Johann Bernoulli, all of them giving their solutions in 1691. The answer is that in coordinates with origin at the low point of the curve and with a parameter a to give an appropriate scale of length, the equation of a suspended cable is y equals the hyperbolic cosine of the ratio x over a. The shape appears both upright and inverted in bridges, hanging cables, and in Finnish architect Eero Saarinen's famous St. Louis arch. Now recall that the circular trig functions satisfy a long and very useful list of identities, and these identities are often tough to prove. Are there corresponding identities for the hyperbolic functions, and are they difficult to prove? The answer is that there is a hyperbolic analog for every trig identity, and they are usually much easier to prove. Here is a reasonably full list of the identities matched against their trig counterparts. The proofs are very easy, essentially based on the properties of the exponential function e to the t. The first identity in the list we've already proved, and the second follows immediately on division of the first by cos t. The addition formula for cos p plus q is proved by a straight calculation. Unlike the circular trig functions argument, we don't need to draw a bunch of triangles based on a circle. So first we write, according to the definition, cos p plus q. Now compute the right side of the given identity to see if you get the same expression. Well, nobody would claim that the proof was elegant, but the two expressions are equal as desired. Notice in that proof above, by the way, that we did use the property that e to the p minus p and e to the q minus q just gives you e to the 0, which is 1. To finish, let's do one simple example. Suppose you know that e to the p is 2 and e to the q is 3. We want to compute sinh p cos p, sinh q cos q, sinh of p plus q, and cos of p plus q. Here we go. Sinh of p is e to the p plus 1 over e to the p divided by 2, equals 3/4. The cos is the sum of e to the p and 1 over e to the p divided by 2, 5/4. The sinh of q is e to the p minus e to the minus q over 2, and that's 4/3, and so on. Now, sinh of p plus q, we use the addition formula. Sinh of p plus q is sinh cos plus cos sinh. Work it out, you get 35/12, And for the cosh of P plus Q, it's the same idea. The cosh of P plus Q is cosh P cosh Q plus sinh P sinh Q, and that works out to 37/12, and you're done.